Hello, I'm Mehdi, postdoctoral researcher from Chalmers University. Today I'm gonna talk about InSAR principle and some talk related to the InSAR nationwide map for Sweden. I've organized my talk into four, let's say, sections. First one related to the project, second InSAR principle, and then InSAR application, and finally nationwide InSAR map of Sweden. The main objective of the let's say ongoing project is related to introducing nationwide ground motion service for Sweden based on the Sentinel-1 at the millimeter level accuracy. The period is between 2015 and 2020. And as you can see from the work packages, among the old packages, let's say the Chalmers University task is validation of the data information. And my task would be to evaluate the accuracy of the InSAR system over the Sweden. Let's say that the main focus of the evaluation process of the InSAR system, the result of InSAR system would be evaluation the system with the independent reference system. It could be GNS system, survey, transporter, corner reflectors, meteorological measurements, and field observation. And also in the next step, we will address InSAR atmospheric correction in order to evaluate the effect of troposphere and univesphere on the, let's say, radar signals. And at the end, we consider the potential for result improvement. InSAR principle, let's say, if we have a satellite, let's say the spaceborne satellite let's say, to monitor the ground surface, when the antenna of the satellite sends signals to the Earth, as we know the speed of light and also the time of traveling the signals, we can calculate the range between the object on the ground and the satellite. And here we can see the, let's say, InSAR geometry. Also, they are working side-looking, mostly in our application, right-looking. And we can see some features of imaging technique, InSAR technique. We can see the swath of the, let's say, the image, or could be the image of size and azimuth directions and flight paths and a slant range. This imaging technique work on the slant range, and we use, in contrary to the, let's say, former real aperture radar, we use synthetic aperture radar, somehow simulating the short length of the antenna and produce us it's a synthetically longer antenna in order to bring better resolutions in SAR images. And now it's time to know that how the SAR data is informed. As you can see on the, let's say, on the right picture, we have an optical image, the high resolution optical image, and the next to it, it's the raw signals. We cannot distinguish anything on the raw signals, but after pulse impression in range and pulse impression in azimuth, the SAR image is formed. And you can see now it's comparable between the, let's say, SAR image and optical image. And on the bottom, you can see the final product that the user can get from the satellites. It includes azimuth directions and in the range directions. And you can see this image includes 3 bursts. And the user will have the amplitude and phase information from the SAR images. And on the down on the left, you can see it's a bit different between the, let's say, the optical image, we have the digital number, and for the, let's say, for the SAR image, we have phase and amplitude, and you can say some mathematical definition for the amplitude and phase, and it's done in the complex, let's say, in the complex A and B, or sometimes called J, and you can see how we can calculate the phase and the amplitude. And after having the SAR data, and now it's time to do some initial processing. First, if we have two images and each has amplitude and phase, and then we need to create our interferogram by applying the first SAR image to the second one, and the first term is related to this part is related to the intensity of the images, and the second one is our interferogram. As you can see, interferogram, the location or spotted, but the location related to the deformation, it creates some fringes. And another important product yielded by initial processing is related to the correlation between two satellites or between two SAR data. And the coherency map is an important one. It's a good indicator that shows us how the level of the noise is in our interferogram. But the main two products of InSAR processing is actually two products. First, we can extract the DEM from the InSAR data and also detect the deformation. On the right-hand pictures, you can see if we have two satellites into two different time steps, and each satellite sends signals, for example, here. Now we are just working on the phase. Phase 1 at the time 1 and phase 2 at the second time. And then if between two time steps, if some object on the ground, for example here, a building, start moving, going down, and it creates, let's say, the high difference between the first and the two building, the phase shift can be detected by received signals. And then we can calculate this shift and convert it to the displacement. This technique is referred to the differential SAR interferometry. But if you want to use, for example, InSAR processing just to extract the DEM, we keep the topographic phase and then we extract the DEM. This technique is also referred to the InSAR interferometry in the InSAR, let's say, community. It's a little difference between the definitions. In differential one, we remove the topographic phase just to keep the deformation information. When we receive the signals from the satellites, the phase component of the interferogram consists of different phase components. And here you can see each of them. First is related to the Earth curvature, and it should be removed from the interferogram. It's caused by the fact that the surface of the Earth is not completely flat, and also it's a little bit curved. And it should be corrected. And on the top here, you can see the corrected one, and on the down is uncorrected. And after corrections, you can see the appearance of the interferogram completely change. And the second terms of the phase is related to topographic. If you want to create a DEM, we extract this phase. But if you want to just keep the deformation information, we remove the topographic phase. And after applying some interferogram and smoothing the signals, and then we need to remove the orbital error caused by orbital inaccuracy of the satellites. And then we have the atmospheric phase. In some cases, the atmospheric phase completely masks our interferogram and should be removed. And the final component is related to the displacement informations, or phase related to the displacements. And you can see the deformation appears here as a fringes. And after unwrapping, we can convert it to the unwrapped phase to the displacement. The main objective here is to get rid of the phase, the first 5 phase components, and just keep the displacement information. So now the InSAR encounter different or 3 main error sources, and we address properly and to remove or somehow mitigate the effect of these error sources on the interferogram. First is related to the phase ambiguity. As I already mentioned in the previous slide, you can see the relation between the phase and the range. And you can see here we have the minus n plus 2p. The main task of unwrapping is to estimate the n, and that's why it's called the phase ambiguity. And it's not an easy task for unwrapping. It's the most difficult part of the, let's say, InSAR parametry is unwrapping, and we need to have a good estimation of n here. And the second source of error is related to the declarations, and here we can see the observed signals consist of change in the look angle, non-parallel orbit, and random motion of the scatterer on the surface. The first two terms related to the, or let's say, called geometrical decorations, and the last term is temporal decorations. And the pictures on the right is the good example of the temporal decorations. And here we can see the same spot of the landslide in north of Italy in Alpine regions. It's related to the landslide called Colvara. And here we can see the same landscape of the landslides in the different time span, in the spring, let's say in the autumn, in the winter time. And we can see the scatterer here, for example, a grass on the ground, constantly changing time to time, and it causes temporal decoration in the interferogram. And in order to overcome this, let's say, problem, if we can, using the shorter spatial baseline and temporal baseline, we can overcome or mitigate the effect of temporal decoration to some extent. The third, let's say, main source of the error in InSAR interferometry is related to the propagation error. And here we can see when the signal of the satellite travels through the atmosphere, it has to pass through the ionosphere and troposphere. And each of this layer has effect of the signals and creates some delay. In the troposphere, especially temporal variation in temperature and in pressure and water vapor cause this delay. And the tropospheric delay can reach up to 15 centimeters on the interferogram. And the ionosphere is usually referred to the number of free electrons between 60 and 100 kilometers above the Earth. And the variation and intensity is latitude dependent. And here we can see the effect of ionosphere on the different wavelengths or sensors. The effect on the long wavelengths, for example, for the L and S band is much higher than the shorter wavelengths, such as C and X band. And for removing or atmospheric corrections in interferogram, as here we can see the atmosphere consists of two main parts, stratified topography dependent component, and turbulence is related to topography. It's a topography independent component. Here you can see the phase delay is summation of the stratified delay and turbulence delay. And for example, here is a good example. This stratified delay created by the GPS plus weather model. And here we have the turbulence component. And after summation both, we have created the total displacement caused by the stratified and turbulence. And here it's our row interferogram. After subtracting the total phase delay from the interferogram, we have the corrected interferogram. And here you can see some deformation signal has appeared. The solution to use these techniques is based on the using ancillary data such as GNSS and weather model and spectrometer data. For example, each of them has drawbacks and advantages. For example, GNSS data, we don't have permanent station everywhere we want to work. And weather model data, the accuracy and the resolution are coarse and it cannot be used everywhere when you want to work locally. And spectrometer, for example, such as Mehdi's data, the problem is temporal sampling and also the coverage of the clouds or case study. One of good option using spatiotemporal filtering and using SAR data in the time series. For addressing each problem, for example, atmospheric, and let's say in the scatterer on the ground, we can use different techniques. For example, permanent scatterer, we can rely on the permanent scatterer on the ground, such as building or any man-made like structure. And for this distributed scatterer, for example, those produce signal backscatter at least beyond the noise level can we get some information from those pixels. For the distributed scatter, we use a shorter baseline, temporal and spatial baseline, which is named as one technique as a small baseline subset, a SPAS. The first one, the PS, will provide us point-wise deformation map, and the SPAS will give us dense deformation map. And here is the short, let's say, summary of how the PS works, PS techniques. Here, first, after creating the stack, we can rely on some permanent scatter on the ground. For example, here you can see some corner of the building and rail guard, and here we can see this scatterer bring or reflected strongly radar signals in comparison with the adjacent pixels, and the phase history of the permanent scatter is stable over the time. That's why we can get reliable information from the PS pixels. And the SPAS, here we can see the graph of the SAR image. On the, let's say, x-axis is the time, and the y-axis is baseline, which is separation between the two satellites on the space. And here you can see the SPAS techniques can create us dense deformation map contrary to the PS techniques. And now it's time to pass on some information regarding the InSAR applications. One of most important applications related to the volcano activity, to monitor the volcano. Here is a good example of Mount Etna displacement. Happened in 2018. On the right, you can see the RAP information in the interferogram, and let's say on the left is ascending and the right is descending. After unwrapping and converting the unwrapped phase to the displacement, here we can see the displacement on the line of sight in ascending and descending mode. And after combining both InSAR geometry, we can create the 2D displacement map, up, down, and west and east. And now I need to explain more about how it's work, the combination of two InSAR geometry. And here we can see this one is related to the descending mode, and this is the line of sight, and this is the ascending mode and the line of sight in these directions. And here we can see we can decompose the, let's say, the displacement vector into two subcomponents for the descending and also for the ascending, and then combine both to create two displacement map in 2 dimensions. Here we can see 2 different InSAR geometry on the object on the ground, and then with combination of both, we will have the 2-dimension displacement in the west and the east, and up and down. And another application is earthquake monitoring. Here we can see a famous co-seismic deformation of BAM earthquake happened in Iran 2003. Here we can see the fringes created by the deformation in the strike-slip fault line. Here we can see. And some fringes created with this movement of the fault, lateral movement. And here you can see, for example, by counting the fringes, we can estimate the displacement. And here we have subsidence, and also the next to the subsidence, we have uplift up to 31 centimeters. And here we can see some observation, field observation, and we can see the line of the faults and the cracks created by the earthquake on the ground. Okay, another good example for InSAR is glacial monitoring. For example, especially for the countries located on the north. And here you can see a good example of some glaciers in north of Sweden, the location called Tarfala, including some major glaciers. I started the data processing in order to monitor these glaciers with the Sentinel-1 within the time span of 2017 and 2019. I used both descending and ascending one, and I used the SBS techniques. And here you can see the final product after combination of two descending and ascending mode. And here you can see the vertical displacement mostly related to the gain and loss of mass ice. And here you can see the horizontal displacement related to the movement or velocity rate of the glacier into the two opposite directions. And here you can see the Glacial is one of the most famous glacier in the world, monitored long-term, more than 50 years. We have good in-situ measurement from these glaciers, and here you can see the mass balance of this glacier for 50 years, and this brings us a good opportunity also for the ice modeler or remote sensing expert in order to calibrate the SAR data for glacier monitoring. And another good example for InSAR application is land subsidence. If, for example, land mostly we would like to monitor the, let's say, residential area in order to monitor the land movement. Here is a good example for the Mexico city. Here you can see the subsidence of land, and here this is up and down movement, and here the lateral in the west and east. And here you can see some evidence shows that the crack on the pavement, and here you can see some, in the perspective, the line is no longer straight and cause cave arc, let's say, caused by the land subsidence. And here we have some subsidence in center of Uppsala city caused by the post-glacial clay. And here we can have the displacement map at London, England, created by the Terrasar. And you can see the red line is related to the underground construction related to the, let's say, tunneling for the train. And we have some blue color and red color here. It's mostly related to the other project. So after, let's say, observing potential at capability of the InSAR, all countries decided to build up the monitoring system using the InSAR. Norway, as a pioneer country in this regard, started first, and after that, other countries followed this routine. And they now, for example, for the Denmark, for the Germany, for the Italy, and the Japan, and now we have the InSAR map in the nationwide scale. And the idea is to take some step further and have a continental InSAR map within the, let's say, Copernicus European Ground Motion Service. The idea is to use the Sentinel-1 data covering all the European country and then create an InSAR map, and then coupling the GNS permanent station in order to calibrate the InSAR map and then integrate both systems together, and then to have the comprehensive InSAR map over the European countries. And here we can see some original consortium and then some private partner engaging in this project. And now let's talk about the nationwide InSAR map. The idea is to use Sentinel-1 data, A and B, into InSAR geometry. And now the system is available and will be accessible soon, hopefully, for the end user freely. The WebGIS system based on the InSAR and created by the Norway, including more than 10 billion measurement points. And as another application, we can, referring to the monitoring mine activity, if we zoom in the location of the Kiruna city, you might know we have a famous mine in this area. And on the right side, we can see this Corina city, and the left side is the mine spot. If we overlay the InSAR displacement map over the city and the mine, you can see the pronounced displacement. As you can see on the right, the color bar shows that between -20 and 20, and you can see the minus value related to the red color shows the increase between the satellites, and the plus number and the blue color is related to the decrease between the satellites and the ground in the line of sight. And due to this activity, the authority make decision to move the city a few kilometers away the mine spot. And after having the initial result of the InSAR system, we decided to evaluate the accuracy of the InSAR, and we decided to compare the InSAR point with some independent measurement as a reference, and hopefully the traffic packet gave me some several measurement point for the buildings within the Stockholm city. And if we zoom in this area, we can see some green triangles. I focus on within the, let's say, red square, and pick up some survey measurement in order to compare the time series of this reference point with the InSAR. If we zoom in this area, we can see some buildings and parking plots. And first, to select the point, I decided to check all the measurement points in the several measurement points to find the one that's experienced some, let's say, deformation. We have at least have some considerable displacement, and then try to find the nearest InSAR point with respect to the location of the survey point. And here you can see the point, the colorful point in the circle related to the InSAR point in the two InSAR geometry, two ascending and two descending with a different track. And I pick survey point A, B, and C. If we look at the time series of both, for example, for A and for B, and finally for the C, at the first glance, we can see that the variation and the trend of the both points is almost agree each other, and we can see a good agreement with the variations. For example, in the A point, we have some, let's say, up and down, which is not agree with the, let's say, with the reference point. And for example, here for the, let's say, for the green and the blue point, you have a good agreement, perfect match. And here also we have a pretty good agreement. If we want to have a better judgment and interpretation in order to evaluate the accuracy of the InSAR, it's better to just fit a linear line to the point and then compare and using some statistical measure. Let's do it. And here we have the fitted line, and here you can see how close both lines are together. For example, in this, for the A point, we have a root mean square error 6.6 millimeters, and we have, for example, for the blue point, we have the almost 1 millimeter differences, root mean square, which is the perfect. And here it seems that there is a bias between two lines. Some consideration should be taken into account to interpret these results. First, we need to know that the InSAR point will provide us a measurement within the pixel size, and the location of the, let's say, the point is not exactly tell us we are having the measurement at that point. It means that the average of the pixel size, which is here, is the single look. We didn't do any multi-looking, is 2 plus almost 50 meters. And the second one is that let's say, we projected the line of sight of, for example, in this case, descending mode into the vertical one. It means that we already assume that there is no any displacement component in the horizontal, and just we have the purely vertical displacement component. which is almost valid assumption in the residential area. But let's say we need to know that if we have the, let's say, horizontal displacement or not. But at least here shows that we don't have that much lateral displacement. But the initial results are promising, and we need to go more further and having more, let's say, investigation in details for accuracy assessments. Thank you for your attention.